Today we're going to take a look at section 4.3, greatest common divisor and least common multiple. And if I remember right on timing, I think the greatest common divisor will finish today, and then least common multiple will be next class period, okay? All right, so to start with, greatest common divisor, or greatest common factor, so GCD or GCF, is the greatest whole number that divides all numbers in a set. Now this next phrase is a phrase we've seen before, but we haven't seen it before. We've seen the property before. We didn't give it this name before. Relatively prime. Relatively prime is two or more numbers whose greatest common divisor is 1. It means they have no factors in common other than 1. Do you guys remember the divisibility rule by 6? Yeah, you're never going to forget it now, are you? Never, ever in your life you're going to forget that rule, right? And the whole idea was that the reason that property worked was because the numbers had nothing in common except for 1, right? Yeah? That's called relatively prime. So any two numbers that have that property, that neither one of them have to be prime numbers. Please don't misunderstand. 4 and 9 are relatively prime, and neither one's prime number, okay? So neither number actually has to be prime for this to be true. They just have to have nothing in common with each other. They are relatively prime to one another. They have no factors in common. Okay. One other comment that I'd like to make while we're here is this is an English comment. You guys know I'm not an English teacher, but I came about this close to being an English teacher. It was English or math, and I chose math. So one of the things that I think you need to be really careful about, and this is a common mistake, is this word greatest here. Greatest does not mean that the number needs to be quite large. Okay? The word greatest is an adjective describing the word common. It's the greatest common divisor. You could say it's actually just describing divisor, but it's the greatest divisor. Let's use divisor. I think that's probably better. Greatest divisor. Divisor's my noun. See, I'm not an English person. This is what happens when you decide not to go that route. You lose things. You will too. You'll lose something along the way. All right. But it's about divisors. So the first thing you have to talk about when you're looking at greatest common divisors is divisors. And divisors are generally smaller than the number itself that you're working with, right? You guys with me? Okay, so the word greatest here does not mean that it's a big number. It is almost always smaller than the numbers you started with. It's just the largest number that divides something. All right? There are several different methods for finding greatest common divisors. The first one we're going to look at is the intersection of sets method. This almost feels like the egg problem we did behind us, where we made some sort of a list. Now, the egg problem was not actually about divisors, it was about multiples. But we made a list of things and looked for things having certain properties. And that's what this actually looks like. You're going to list all the divisors of each value, and then you're going to find the largest number that's in common to all the lists. Okay? So we're going to do an example, and we're going to do an example with the numbers 12 and 15. So we're going to list all of the divisors, not just primes, like all of them. All the divisors of 12, all the divisors of 15. So the first divisor in any list will be 1. That's always going to be there. What comes after 1 when you're dividing by 12, or dividing the number 12? 2, and then 3, and then 4, 6, and 12. And you don't necessarily have to do them like in order. We could have done them in pairs. Like I might have seen this and said, okay, we talked about this before, so this is 1 and 12, and then I've got 2 and 6, right, putting them in ordered pairs basically, and then 3 and 4. So if you want to put them in pairs of numbers, that's fine. Let's do the same thing with 15. I'll put them in pairs because I like that approach too. So we'll start with 1, it'd be 1 and 15. What else do we have? 3 and 5, and that's it. And we compare these lists of numbers, this one and this one. And we say, what is the largest number in both lists? And the answer to this one is 3. So the greatest common divisor, and I'm going to write some notation because we're going to need it later anyway, of 12 and 15 equals 3. Okay, so GCD, the parentheses tell you of which numbers, the greatest common divisor of which numbers, 12 and 15. And there's nothing special about having 2 numbers. You could have 3 numbers or 4 numbers or something like that. Greatest common divisor of 12 and 15 is 3. This list method is great when the numbers are small. Right? No problem. It was fast. It was easy. You knew those factors. It was no big deal. But if you had the number 352, all of a sudden the problem becomes a lot more challenging because I don't know all the numbers of 352 right off the top of my head, right? Okay, so we're going to do another method. Second method we're going to look at is prime factorization. Prime factorization has more steps involved. Generally works a lot better for larger numbers though. So the first thing you do is you construct the prime factorization. Notice the word is prime here. The prime factorization of each number. After you get the prime factorization, you choose all the prime factors that are common to each factorization. That starts to feel a lot like the other problem on the board right now too, right? We looked at everything they had in common and we factored it out. Same kind of idea. Okay, what do they have in common? And then we list the exponent that is the smallest, right? That's what we did over here too when we factored it out. We said, okay, well, one of them has 2 and the other one has 1, which means that most they have 1 in common. So we used the smaller exponent. And the last step that we didn't do over here in this particular problem was we actually go back and we multiply those values together. Okay? It's kind of like this. Whatever the problem starts in is how the problem should end. So if the problem starts all factored out, then it makes sense for the answer to be all factored out. If the problem starts out as 3,462, then we want the answer to be in that kind of a form, just a whole number or natural number form. Okay? All right, so we are going to use a little bit larger numbers this time and do an example. Did everybody get everything written down on this slide? Fabulous. Okay, so we're going to use the numbers 400 and 360. And you can do factor tree if you prefer. I am a real big fan of this division that goes downward, this division step, so that's what I'm going to do. 400 is divisible lowest prime value by what? 2. And then I get 200. And I'm going to keep dividing by 2 until I can't any longer. So 200 divides by 2 to give me 100, which divides by 2 to give me 50, which divides by 2 to give me 25, and then it can no longer divide by 2. Clearly can't divide by 3, but I can divide by the 5s. So I get 5 and 5. I've got all prime factors when I'm done. And my prime factorization factors are over here. I did this last time. And we are going to write down the prime factorization. So this is 2 to what power? How many 2's are there? 4. And how many 5's are there? 2. Okay, so I'd like for you guys to do 360, either with a tree or with the division steps down. Go ahead and do that one, and then I'll fill mine in. And write the prime factorization at the bottom underneath it, just like I did under the 400. Okay, so I wrote mine up here as I saw that most of you were finishing yours up. Did everybody get a factorization that looks like this? 2 cubed times 3 squared times 5. Okay, that's step 1 of the division method over here that we talked about, the prime factorization method. Step 2 is to choose the prime factors that are in common. So if you take a look at these lists of factors here, I'll put them in boxes in red. What factors, that is, what primes do they have in common? 2, and what else? 5. Now, legitimately, that may be your answer, 2 times 5. But we haven't actually done step 3 yet. Step 3 says then to look at the lists again and look at the exponents on them. So how many 2's are there in the first list? There are 4. How many 2's are in the second list? 3. Which of those numbers is smaller? 3. So the 2 will have a exponent of 3, an exponent of 3. Okay, whichever one's smaller. But you don't just eliminate it and just use the number 1. You use whichever one's smaller. And then on the 5s, this one has 5 squared, and this one has nothing up there beside the 5, so it's understood to be a value of 1, right? So our 5 will have an exponent of 1. Now, this is the answer, but it doesn't really look like the question began. So we're going to figure out what this simplifies into if we multiply back out. What is 2 cubed? 8. It's 8 to the 4th 16, yeah. And then 8 times 5 is 40. Now, it would be a good idea when you get your answer to really make sure that it is a divisor of the 2 you started with. I mean, does 40 really divide 400? Does 40 really divide 360? Yes, well, at least we've got a divisor. That's good, okay? Now, that doesn't guarantee in our minds that it's the greatest one, but it at least guarantees that it is one. It gives us sort of a half-check step, okay? If you'd gotten 42 here and you looked back at the original values and you would be like, that didn't work, you'd know you'd make an error at least, okay? Yeah. Okay, any questions on this method? This is called the prime factorization method. Not to be confused by the division of primes method. You guys have a note card on your test, right? To remind yourself which one's which. Division by primes is our next one. This is probably my favorite method. It's not one that I grew up knowing, but I really like it quite a lot. What we do is we write the numbers in a row, and then we divide the numbers by a common prime factor. And notice it says A. A common prime factor. It doesn't have to be the smallest one. It might be. But it might be that you notice they're both divisible by 5 before you notice they're both divisible by 3 or something like that. That'd be okay. We divide those quotients by another common prime factor, and we keep repeating this step. We keep dividing by common prime factors as long as there is one. Okay? And then the greatest common divisor is the product of the primes. Okay, so let me go back. Well, you know what? Let's do the problem first. And then I'm going to compare these last two methods so I can kind of explain to you why I like this one a little bit more than I like the last one. Okay? Does everybody have all these details written down? Are we good, Gretchen? Okay. All right, same numbers, I think, as that I had before. Oh, they're close. They're not the same. They're close, though. What we're going to do is we're going to write them sort of next to each other. You can put a little space in between them, but they're on the same line. And we're going to do one giant division like this. And what we want to do is we want to look at these two numbers and say, what prime number do they have in common? So somebody give me a prime number that they do both divide by. 2. Okay. So if I divide 410 by 2, what do I get? 205 is right. How about 360 divided by 2? 180. And for the purposes of what we're doing here, if you want to grab calculators out, that's fine. All right, another prime number that divides both these numbers. 5. All right, now 205 divided by 5. 41. And 180 divided by 5. One's 36. Okay, now you may not know, I mean 41 is a little bit larger than some of the ones we've worked with. You may not know, is 41 prime or not? It is prime, okay? It is prime. If you weren't sure though, how far up the prime number list would you have to go to check?
6.
So why did you say 6, Alyssa? You're right. Yeah, you square root it. So if you square root the number 41, what does your calculator tell you?
6.403.
Okay, so 6.4. What is the closest prime number under 6.4? It's actually 5, isn't it? So all we need to check is to make sure that 41 and 36 are not both divisible by 2, 3, and 5. And they're not. At least 41's not divisible by those, right? So we stop right here. The answer to the question is these numbers that we've divided by. So the greatest common divisor here is 2 times 5 or 10.
Do we need to put in parentheses?
I don't care whether or not it's there. I think you're asking me whether or not I should have done something like this.
Yeah.
It's perfectly fine that it's there. I'm a little bit just more concerned that if you see the notation, you know what it means, than that you use it consistently. Because the only values we have in this problem are these two values. So if I leave them off, it's understood that it's the greatest common divisor of what I'm doing. In fact, if you'll notice over here on this one, I didn't even write down GCD equals on this one, did I? I really didn't. I just want to make sure that when you see the notation like this, you know what it's referring to, because occasionally your book will use it. Okay, so let me tell you kind of why I'm a fan of this method compared to the other method, at least a little bit. This method over here, can't get back to it, there we go. It's beautiful. I mean, like, it's organized lists, and part of my heart just says, oh, I love this list method thing. I love it going on. The reason it's not my favorite is because you end up doing more work than you needed to do. I mean, really, did I need to know the prime factorization of those actual numbers in order to find my answer? Not really. I really didn't need to know that much of that information, right? Like, if I did prime factorization with these numbers, that 36, I wouldn't have stopped at 36. I would have divided the 36 again by another 2, and then again by a 3. I would have kept going. Did I need to divide the 36 by anything else to get the answer to this question? No, I really don't. I don't need to know what the factors of 36 are. Because when I got to the point where it's 36 and 41, I knew I was done. Yes, ma'am.
Do you have to use primes? Because they could look at those and just say that both of them are divisible by 10. I know that, and then you can see, okay, I get 41 and 36 after that.
It's a very good question. So the technical answer is yes, you have to use division by primes. And the reason is because it's the title of this description. Now, the true answer to does it work if you don't is yeah, if you divided by 10 or by 7 or 14 or numbers that weren't prime, would it still be okay and give you the right answer? Yeah, it still would. We're going to use primes just because that is the name of their method for doing that. But technically, yeah, the primes are a kind of an unnecessary feature in what's going on. Yeah, it's kind of like saying when I do my prime factorization like this, do I really have to go from smallest to largest by divisibility of my prime numbers? Not really. I mean, but it's very nice in the end that they are all sort of in order like that. I mean, it's kind of friendly. But, I mean, I'll still get the same answer if I do it in a different order, right? It's almost like that. Okay, one last method. This one feels very much not like the other ones. Very different. Euclidean algorithm. You take the larger value and you divide it by the smaller value. What you care about is the remainder, not how many times it actually goes in. You use the remainder and the number you originally divided by, and you do it again. And you keep dividing the remainder and the number you divided by until you end up with 0 as a remainder, and then the answer is the last number you divided by. It's a very different kind of method. It's really not that difficult to do. I'll show it to you here in a second. But it feels so much not like the other ones. I mean, it doesn't even make a, sort of like confuse it with something else. You're not going to confuse this with anything else. There's nothing else that we do that has this sort of feel to it. Okay, you guys ready to see an example of this one? Okay. 72 and 126. All right, so we're going to do the division. You always have to divide the bigger number underneath, the smaller value on the outside. So this will be 72 divided by 126. Okay? How many times will 72 go into 126? Just once. What is 126 minus 72? 54. Okay, so what do I use? Now I use the remainder. It's all about the remainder. And the divisor from that same problem. These are the two numbers that I use. Now, the remainder better be smaller, otherwise it's not really the remainder. You guys catch that, right?
Yes.
Okay, the remainder has to be smaller. So the remainder will actually be the number that will go on the outside now. Whoops, didn't mean 24, I meant 54. And the number that used to be the quotient, right, or not the quotient, the divisor, will now be the dividend, the number that goes underneath. It's still biggest divided by smallest, but these are the numbers you're using now. So how many times will 54 go into 72? Well, just once, right? When we subtract 54, so what's 72 minus 54? 18. It's all about the remainder. 18 I care about, and the 54. That's all I care about. And I do it again. And this really is the remainder because it's smaller than the divisor. 18 on the outside, 54 underneath. So how many times will 18 go into 54? 3. And 3 times 18 is 54, which gives me a remainder of 0. So this tells us that we're done, right? The remainder of 0 tells us that we're done. And then the question is, okay, well then what is the answer? Well, the answer is the last number you divide it by. So the GCD is 18. I think there's a proof in your book. Nobody's ever actually asked me to show it in class. It has to do with the way you're grouping things together, and I've seen a proof before, but I have not done it in a while, so I'm not going to try off the cuff here. Eventually, yes. Now it may be that at the very end you had to divide by 1, right? Could you end up having to divide by 1? You could. In which case your divisor, your greatest common divisor, could be the number 1. So that could happen. What's that?
Well, if they end up dividing by 1, then it doesn't technically mean they have no.
Well, it means that they're relatively prime, and it means their greatest common divisor is 1. So they have a greatest common divisor. It's just that it's a value 1, which is not a very helpful greatest common divisor. Yeah. All right, I've got a few more minutes left, so let me kind of give you some ideas about things that are applications of this information, okay? So I think maybe we have some later on in this section. You'll certainly have some in your homework and things like that. But you might actually think of yourself, okay, well, where would I have seen a problem like this about finding divisors of things? Well, think about what happens when you're trying to arrange cupcakes on a plate or on a tray. You have 24 of them. What are your options? 6 by 4 and 4 by 6, right? You're trying to make it so that the rows and the columns have the same number of things, right? Let's say that you had multiple kinds of cookies. This is an example I've seen people use before. So let's say you had chocolate chip cookies and you had oatmeal raisin cookies, all right? And you do not want to put them on the same plate because they look a little bit alike. If you don't like oatmeal raisin, you get one of those oatmeal raisins, that's not going to be very fun, right? Yuck. I don't like oatmeal raisin. So you want only oatmeal raisin or only chocolate chip on these different plates of cookies that you're going to have sitting out. Well, how many oatmeal raisins, how many chocolate chip are you going to make? I mean, how's that going to happen? Well, let's say you had 30 of one and you had 24 of the other. You had 24 chocolate chips and you had 30 oatmeal raisins, and you want all the plates to have the same number of cookies because that's what it should look like when you start at, at a party. It should all be even. So how many should you put on each plate? Well, the answer would be 6 because that's the greatest common divisor. It's the biggest number that I can divide 30 and 24 both by so that I get the same. Now, I don't have the same number of plates of cookies, right? That's not going to work. But I do have the same number on each plate like that. So those are some examples. Your book's got some other examples. I think it might do something with pencils and rulers or something like that. I can't remember. But we did one, and it wasn't in this section. It was back in section 4.1 with, I think his name was Mr. Arbor, and he was planting trees. Do you guys remember Mr. Arbor? And he was planting trees, kind of like my cupcake example on the rows and the columns on the cookie sheet or something like that. And so we have things like that, okay? So, all right, that's it for today.